So at CitizenCon 2016, we were supporting spherical terrain, seamless transition, runtime generation at 60 frames per second without any pre-processing, unrestricted view distance and planetary scale, plus different ecosystems, and the first version of procedural vegetation, as well as hardware tessellation and per-pixel displacement. Going back in time a bit before Gamescom, here is a test showing how Pascal had quickly put together a Mars-looking planet, using a few ecosystems and changing some parameters like atmosphere colors and so on. So with just a few ecosystems and painting them on the planet through the Planet Editor, we can create many different types of environments and planets. Here I'm showing a bit of our work in progress features. One of the next steps for us is improving the procedural vegetation placement and object distribution. In this video clip, you can see trees and grass being rendered through the zone system, which Chris Bolt is going to talk about in a bit. So here you can see in this last video another work in progress feature, a rotating planet. The planet is actually rotating extremely fast, but at this scale, looks like it's not moving. But if you get very close, on top of this large static control tower, which is not moving, we can see the planet rotating very fast. Another interesting thing to notice is the ocean, which was worked on by Anis, one of our new hires in Frankfurt. The ocean is reusing the planet terrain patches with different displacement. This way we're getting adaptive subdivision computations for free, and we don't even need any extra geometry, memory usage for the ocean.
The original ocean was also just a flat terrain piece, more or less. And of course, for the planet, we also needed this to be a spherical object. And this feature made it in. You can see that we have proper waves, there's vertex animation, it's nicely tessellated, the shading is working. Anis has really put a lot of work into it. And the next feature would be the clouds. The clouds are still in a very early stage. Carsten Wenzel is putting a lot of work into it, doing a lot of research, but you can already see some realistic behavior. You can see they are casting shadows, there are different thicknesses to them in certain areas, so there's less light penetrating. And speaking of light, one thing that also changed quite a bit is the sun. Because this is a spherical object, you have different kinds of lighting all over the planet. So you cannot just simply say, okay, for this planet, I want to have daylight. I want things, whatever is happening on the planet, to take place in sunset. Because depending on where you are on the planet, you have different lighting situations. And all this is now implemented depending on where you are. The atmospherics generate different effects. At the sunset, obviously, everything turns red. And during daylight, you have a blue bounce light from the sky and all this type of stuff.
Hello everyone, I would like to talk to you about the changes we did to our core technology, which allowed us to implement the planets as you have seen them during CitizenCon. One of the first components we changed was the job system. This system is responsible to distribute work, which must be done to compute a frame in a video game over multiple CPUs. This work is called jobs in our engine. The old approach was applicable for perhaps 3,000 to 5,000 jobs per frame, whereas the new one we can handle a very larger armor. This was realized mainly by utilizing the inherent parallelism of games, which is basically the smart way of saying that we have always more than one object to update. Furthermore, we changed the job system to better communicate with the operating system to allow for better usage of the available resources. We then built the zone system, which is a spatial object management system. Such a system is responsible to allow an efficient way to query objects based on spatial properties, for example, finding objects visible inside a camera or overlapping with a box. This system initially replaced the old octave-based culling approach and is now used to store all kinds of objects within the world space position. This system had two important characteristics. Being efficient, the system should scale well. We already have over 200,000 vendor-able objects present in Crusader. This is realized by ensuring that we use efficient data structures and use a processing layout which maps well to multiple cores with the help of the job system. Then the system should cope very efficiently with large clusters of simultaneous moving objects. Here we use a novel approach of using multiple reference frames. The regular approach used in games is to store objects in a single coordinate system, the so-called world space. This world space position is then sent to the GPU as 32-bit coordinates and projected to the screen with a projection matrix. For Star Citizen, we cannot use this approach due to two reasons. The GPU can only process 32-bit floating point positions efficiently, but we need 64-bit positions for our large game world. We want to move kilometer-long spaceships and planets through space. In the old approach, this would mean updating the positions of all objects on, say, ships or planets, which is not possible in real time. So we did something else. At the highest level, we organized our world in a 64-bit position universe coordinate system. To render the object stored in it, we compute a camera relative position before we send the data to the GPU. This allows us to keep the whole world as one coordinate system by using the more efficient 32-bit position on GPU. To move objects around, we use multiple zones. A zone is its own coordinate system and hosts all objects which move together, like a spaceship or a planet. With this design, we can move an arbitrary large number of objects by just moving around the pivot of the coordinate system. Culling in such a system is implemented by converting the tested against objects into the zone space. This sums up the technologies we had to advance for our goal of a living universe. Thank you.